Dear Professor and TA, we are Cai Zixian and Guo Chunsong. The topic of our final project is the two-dimensional icing model simulation. In this project, we are going to simulate the two-dimensional icing model using different algorithms. The two-dimensional icing model simulates the behavior of atomic spin on a two-dimensional lattice whose shape is a square. And each entry on the lattice is an integer, which is either +1 or a -1. The sign of this integer represent the direction of the spin of the atom on this lattice. The spin direction of each entry will change over time based on the spin direction of the other entries on the lattice. And the two-dimensional icing model is going to simulate such a change of the spin direction in order to find the properties of atomic spin on the two-dimensional lattice. In our project, we implement the Wolf algorithm and the Swedenson-Wang algorithm. And first, we will estimate the critical temperature by the values of magnetic susceptibility and the Binder cumulant. And next, we will find the relation between the thermal capability and the size of the lattice. And lastly, we will compute the autocorrelation of Wolf algorithm and Swedenson-Wang algorithm. We now introduce the Wolf algorithm and the Swedenson-Wang algorithm. A step in Wolf algorithm is as follows. First, they will construct a cluster C with a randomly selected spin I in a grid. And then they will select an unvisited spin S in C and mark S as visited. And for each of the nearest neighbor S prime of S, if the direction of spin are identical and S prime does not belong to the cluster C, then S prime will be added to C with a given probability. And step 2 to step 4 will be iteratively processed until there is no unvisited spin in a cluster C. And after all the spin in the cluster C is visited, all the spin in C is flipped. This is a swap in the Wolf algorithm. And a swap in the Swedenson-Wang algorithm is as follows. If we have a lattice, they first Swedenson-Wang algorithm first assign an edge with a given probability to each of the nearest spin pair on the grid. If the spins in the spin pair have the same direction of spin. And after the edges is assigned, there is a graph on the lattice. And for each connected component in this graph on the lattice, the Swedenson-Wang algorithm will flip all the spin in it with probability 0.5. And now we will start introducing our experiment. We will run each algorithm for 5,000 swaps, 50,000 swaps, and we will discard the first 5,000 swapped to thermalize the lattice, and the size of each spin is 100. For the magnetic susceptibility from the Wolf algorithm, we can see that when the side length of lattice is 128 and 256, the magnetic susceptibility increase uh, near 2.27 and 2.28, but which is uh, where the critical temperature is near the 2.27. But we do not see such an increase of magnetic susceptibility when the side length of the lattice is 1672, 1632, and 64. And for the magnetic susceptibility using a Swedenson-Wang algorithm, we can see the same scenario. The magnetic susceptibility increase when the side length of lattice is 128 and 256, but the magnetic susceptibility remain almost the same when the side length is 16, 32, and 64. Next, we look at the Binder cumulate. The Binder cumulate derived from Wolf algorithm. Using different size of lattice crossed at a point that is very close to the critical temperature, which is 2.2692, as we can see in the figure 3. And for the Swedenson-Wang algorithm, we achieve the same result. The Binder cumulate using different sizes of lattice will intersect at a point that is very close to the critical temperature. And for the thermal capability, we found that when the lattice size is 16 and 32, the thermal capability is a constant multiplied by the size of the lattice over different temperature. However, we found that the thermal capability will goes from 1.5 to 2.5 multiplied by the size of the lattice when the side length of the lattice is 64. And this result is derived from the Swedenson-Wang algorithm. Next, we look at the autocorrelation of the Wolf algorithm. We can see that for every of the lattice sites, we can see that the autocorrelation of Wolf algorithm is very low, even the time step is very short. For example, when the time step is 5, the autocorrelation of Wolf algorithm is no more than 0.05 and negative 0.05. And for the autocorrelation of Swedenson-Wang algorithm is very small. It's very small as well, but we can find that the autocorrelation of Swedenson-Wang algorithm will be more stable in the beginning. It will be most stable when the time step is short compared to the Wolf algorithm, which is over here. But as the time step increase, the Swedenson-Wang algorithm is more fluctuate. more than the Wolf algorithm. In conclusion, we use two efficient algorithms, the Sweaterson-Wang algorithm and the Wolf algorithm, to simulate the two-dimensional icing model. And the magnetic susceptibility will increase near the critical temperature, and the cross point of binaccumulate over different sizes of lattice is close to the critical temperature. And for the thermal and we found that the thermal capability is proportional to the lattice size. And the autocorrelation of both Wolf and Sweaterson-Wang algorithms are small with a short time step. And the autocorrelation will be smaller when the time step is small in the Sweaterson-Wang algorithm. And when the time step is long, the Wolf algorithm will have a smaller autocorrelation time. And this is the end of our presentation. Thank you for listening.